Hello, in this video we will be looking at a three-phase transformer example. In this example we'll look at how to get the parameters of the three-phase transformer and then finding the voltage regulation and efficiency. Right, so we have in this example a three-phase 50 kVA 660 415 volt delta Y transformer bank. Two tests were conducted on the transformer bank to determine the parameters, and the test data are given: test A voltage, current and power, test B voltage, current and power. And it's known that the transformer is supplying 415 volts to a village, and the village is drawing 28 amps during the day and up to 45 amperes during the night, with a typical power factor of 0.87 lagging. So what they want us to determine is the voltage regulation and efficiency of the transformer under maximum load conditions. Right, so because this is a three-phase transformer and we're given some information, so let's extract the information first. You're given 50 kVA. Please remember that this is the rated apparent power of the transformer. And it is a three-phase, it's a three-phase rated apparent power. Okay, and then we have the rating 660/415. So that means the primary voltage, primary line voltage, VP line rated is 660 volts, and VS, the secondary voltage, line voltage, VS line rated is 415 volts, and it's a delta Y connection. So delta Y means delta connection on the primary side and Y connection on the secondary side. Alright, so if we want to find the turns ratio of the transformer, the turns ratio A will be VP phase, the phase voltage on the primary side rated, over the secondary side phase voltage rated, VS phase rated. And to do that, we must look at the connection. So delta connection on the primary side. So therefore, VP phase rated will equal VP line rated due to the delta connection. So it's just 660 volts. But it's a Y connection on the secondary side. So therefore, VS phase rated will equal VS line rated divided by square root of 3. So 415 divided by square root of 3. And this will equal 239.6 volts, and that will give us a turns ratio 660 over 239.6, a turns ratio of 2.75. Now then, we are given the test information. Now what you must understand from the test information is all voltages and currents are given as V line and I line. That means all voltages and currents are line voltages and line currents, and the power given, the power is a three-phase power. Right, so what we're going to do next, we're going to find out which one is the open circuit test and short circuit test from the test A and test B. Then, before we can get the voltage regulation and efficiency, we must first find the equivalent circuit parameters. So before we can solve the question, we must first find the equivalent circuit parameters from the test, and then we can calculate the voltage regulation and the efficiency. Right, so let's do that. Okay, so let's start by finding the equivalent circuit parameters. We have two tests, test A and test B. So one of it will be the open circuit test and the other one will be the short circuit test. What we've learned is For the open circuit test, we need to check the voltage from the test data. And please remember, the voltage is a line voltage. So if the line voltage given in the test data is equal to VP line rated, so if the line voltage given is equal to VP line rated, then the test was done on the primary side. But if the voltage given from the test is equal to VS line rated, then the test was done on the secondary side. Then from the open circuit test, we're going to determine YE, and from there we'll get the RC and XM, or RC prime and XM prime. Now we have these two test data, test A and test B, so let's look at the voltage. So for test A, the voltage is 55 volts, and for test B, it is 415 volts. So looking at these two values and comparing with the rating, so VP line rated is 660 volts and VS line rated is 415 volts. So here we can clearly see test B, V line is 415 volts, and this is equal to VS line rated. So therefore test B is the open circuit test done on the secondary side, because V line is equal to VS line rated. Okay, so we now determine that test B is the open circuit test. Before we can use the values in this formula here to find YE, we need to get VOC phase, IOC phase, and POC open circuit for one phase. OC is open circuit. But we're given 415 volt. This is the open circuit line voltage. 4 amperes, which is the open circuit line current, and 1200 watts is the open circuit three-phase power. And we have to remember test B is on the secondary side, and the secondary side has a connection, Y connection. So there's a Y connection on the secondary side. So therefore we are having a Y connection because test B was done on the secondary side, we've just determined just now. So VOC phase will be equal to VOC line divided by square root of 3. So 415 divided by square root of 3 is 239.6 volts. And the current given from the test B is 4 amperes. And because it's Y connection, the open circuit current phase current is equal to the open circuit line current, so it's just 4 amperes. And the power given 1200 watts is 3 phase, so to get one phase, the 3-phase power divided by 3, so 1200 watts divided by 3 is equal to 400 watts. Now using these values that we've just obtained for VOC phase, IOC phase, and POC single phase, we can put it into this formula to find the YE. And once we have YE, we can find RC prime and XM prime, because this test was done on the secondary side. Right, so we've determined just now that the test B is the open circuit test done on the secondary side, because 415 volts from test B is equal to VS line rated. And because of the Y connection, we got VOC phase of 239.6 volts, IOC line was 4 amperes, so IOC phase is equal to 4 amperes because of the Y connection, and the open circuit power single phase is 400 watts. From the 3-phase power, we divide by 3. Now that we have all these values for VOC phase, IOC phase, and power single phase, we can substitute into this formula to find YE. So YE, the magnitude is the single phase current divided by the phase voltage, so 4 divided by the phase voltage 239.6, and the angle is negative inverse cosine single phase power 400 over the voltage, phase voltage 239.6, and the phase current 4 amperes. That will give us YE in polar form of 0.0167, angle negative 65.33, but we need to convert this into rectangular form with real and imaginary parts. So 6.97 times 10 to minus 3 minus J 0.0152. Now the real part, we know from our previous knowledge, our previous learning in class, is equal to 1 over RC prime, and the imaginary part will equal 1 over XM prime. RC prime and XM prime because the test was done on the secondary side. So now we can find RC prime by taking the inverse of the real part. So 1 over 6.97 times 10 to the minus 3, giving us an RC prime of 143.47 ohms. And taking the inverse of this imaginary part will give us XM prime. So 1 over 0.0152, giving us an XM prime of 65.79 ohms. Right, now that we have RC prime and XM prime, we can go on to the short circuit test. Right, so we've known that test B is the open circuit test. So that means test A is the short circuit test. But what we need to know now is which side was test A conducted. Now, in order to know which side is conducted, we need to check at the current given in the test data, which is here 70 amperes. We need to determine if this current is equal to the IP line rated or IS line rated in order to know which side the test was conducted. Now, to find IP line, the primary line current rated, we can get this from the rated apparent power of the transformer divided by square root of 3 and VP line rated. This is because, if you remember, the S is equal to square root of 3 V line, I line. So we rearrange to get the I line. So IP line rated is equal to the apparent power rated divided by square root of 3 VP line rated. And we substitute the value for S rated is 50,000 and VP line rated of 660. This gives us a rated primary line current of 43.74 amperes. And for the secondary side rated line current, we'll use S rated divided by square root of 3, but now VS line rated. And substituting the values, we get 50,000 divided by square root of 3, VS line rated of 415. That gives us a rated line current on the secondary side, IS line rated of 69.56 amperes. Now, comparing with the test data, the test gave I line from the test. I line is 70 amperes, which is very near to IS line rated. So therefore, test A is the short circuit test done on secondary side. Okay, so to check for the short circuit test, we need to look at the current given and compare it with IP line rated or IS line rated to know which side the test was done on. Now that we've determined test A is a short circuit test done on the secondary side, and we know that the secondary side is has a Y connection from the information given in the question. So therefore, we need to find the short circuit phase voltage, short circuit phase current and the short circuit input power single phase. Okay, so due to the Y connection, the value given 55 volts is actually the short circuit line VSC line voltage, and because it's Y connection, we need to divide by square root of 3. So 55 divided by square root of 3, that gives us a voltage of 31.75 volts. This is the VSC phase. And the 70 ampere given in the test data is ISC line current, and because of the Y connection, it will be equal to ISC phase, so it's just 70 amperes. And the power given in the test data, 855 watts, is the 3-phase power for short circuit test. So we need to divide this by 3 to get the single phase power. So 855 divided by 3 is 285 watts. Having the values of VSC phase, ISC phase, and single phase power, we can now use this formula to find ZSE, and from ZSE we can then find REQS and XEQS. Right, so from our VSC phase of 31.75 volts, ISC phase of 70 amperes, and PSC single phase of 285 watts, let's now calculate ZSE from this formula. And ZSE is the voltage divided by current, so 31.75 divided by 70. And the angle of ZSE is the inverse cosine of the power single phase, 285, divided by the voltage and divided by the current. So this gives us ZSE in a polar form of 0.454 with an angle of 82.63. And if we were to get this in rectangular form, the real part will be 0.058 plus the imaginary part J 0.45 ohms. And as we've learned before, the real part will equal REQS and the imaginary part will equal XEQS because the test was done on the secondary side. So therefore, REQS is 0.058 ohms and XEQS is 0.45 ohms. And from the open circuit test we got previously, RC prime was 143.47 ohms and XM prime 65.79 ohms. So now we've got all the parameters for the equivalent circuit of the 3-phase transformer. Having the equivalent circuit parameters, we can then answer the question to find the voltage regulation and efficiency at maximum load. Now that we have got the parameters of the equivalent circuit, let's just recap. The test B was done on the secondary side, the open circuit test, and test A, the short circuit test, was also done on the secondary side. So we can draw the equivalent circuit parameters in the equivalent circuit, and the equivalent circuit to be used is the equivalent circuit referred to the secondary side, okay, because both the tests were done on the secondary side. And take note that the equivalent circuit of a 3-phase transformer, this is a 3-phase transformer. In the 3-phase transformer circuit, you must use phase currents and phase voltages. Okay, that's the difference between 3-phase transformer circuit and single-phase transformer circuit. Now let's write down the parameters of the equivalent circuit. RC was 143.47 ohms. XM was 65.79 ohms. REQ 0.058 ohms and XEQ 0.45 ohms. Now the transformer is supplying a village at 415 volts and the current drawn from the transformer is 28 amps during the day and 45 amps during the night time with a power factor of 0.87 lagging. So if you were to connect the load to the transformer, the load is at the secondary side and the load is the village. The voltage at the load is 415 volts And the magnitude of the current drawn by the load is between 28 to 45 amperes, and the power factor of the load is 0.87 lagging. What they want is to find the voltage regulation and efficiency at maximum load. So let's look at the maximum load condition. So at maximum load, the voltage Vs line will equal the V load, which is 415 volts at angle of 0 degrees. Okay, the voltage given is always a line voltage at the load. So in order to use the circuit, we need Vs phase. So due to the Y connection, remember the connection on the secondary side is a Y connection at the secondary. So therefore, Vs phase will be Vs line divided by square root of 3. So 415 divided by square root of 3 is 239.6 at the angle of 0 degrees. So that is the Vs phase at maximum load. And at maximum load, the magnitude of the load current is 45 amperes. We take the largest one, that's the maximum. And the angle of the current at the load, we get it from the power factor. So inverse cosine 0.87, but negative because it is a lagging power factor. And that gives us an angle of So inverse cosine of 0.87 gives us an angle of negative 29.54 degrees. Negative because of the lagging power factor. So therefore, Is phase will equal the I load, because this is a Y connection, and that gives us a value of 45 angle negative 29.54 degrees. Why we need this Vs phase and Is phase is because in order to find voltage regulation, the formula is Vp phase over A minus Vs phase over Vs phase. So before we can get the voltage regulation, we need next to find Vp phase over A. So in order to find the voltage regulation, the formula of Vp phase over A minus Vs phase over Vs phase, we need to get the equation for the transformer to find Vp phase over A, and from the equivalent circuit, if we do KVL on this part of the circuit, then Vp phase over A, which is this voltage, is equal to Vs phase plus the voltage drop at Req and Xeq. So Is phase multiplied by Reqs plus Jxeqs. And we had from our previous calculation, at maximum load, Vs phase was 239.6 angle 0. Is phase was 45 angle negative 29.54 at maximum load. And Req 0.058 plus Xeqs 0.45. So from here, we can calculate Vp phase over A, and it comes out to be 252.38 at angle of 3.71 degrees volts. Now we can find the voltage regulation at maximum load. And the voltage regulation, we just take the magnitude of Vp phase over A, 252.38, minus the magnitude of Vs phase, 239.6, divide by Vs phase magnitude, 239.6. And we multiply this by 100% to get it in percentage. And this gives us a voltage regulation value of 5.33%. Okay, so in order to calculate voltage regulation, you need to find VP phase over A, and the formula for VP phase over A for the transformer is by having the KVL on the secondary side. So VP phase over A is equal to VS phase plus IS phase multiplied by REQS plus JXEQS. So don't forget, when you're using the equivalent circuit, you must use phase voltages and phase currents. Right, so next we will look at calculating the efficiency at maximum load. Now that we have the voltage regulation, we've come to the last part of the question where they want us to calculate the efficiency of the transformer when supplying the village at maximum load. So from our previous calculations, we have got the equivalent circuit parameters RC, XM, REQ, and XEQ from the test A and test B. Okay, and once we had the equivalent circuit parameters using the equivalent circuit and the conditions of the load, remember the load is connected here, which is the village. So we found that at maximum load, the VS phase is 239.6 angle 0, the IS phase is 45 angle negative 29.54 amperes, and the VP phase over A we calculated to be 252.38 angle 3.71 volts. Now, to find the efficiency, the formula for efficiency is P out over P in times 100%. But for the transformer, we calculate P in using the P out plus the losses, and the losses in the transformer is the copper loss, PCU, plus the core loss due to the hysteresis and eddy current in the transformer. So to get the efficiency, P out over P out plus PCU plus P core, and we multiply this by 100%. So that is the formula for efficiency. Now, in order to find P out, for the three-phase transformer, P out is 3 times VS phase times IS phase times cos theta. So in this case, we take the magnitude of VS phase and IS phase. So 3 times the magnitude of VS phase, 239.6. The magnitude of IS phase, 45. And cosine of the angle of the current. The angle of the current will be the theta. So cosine of 20, we can just take the magnitude of the angle, 29.54. So we calculate that to be P out 281.41 watts. That is the output power for the three-phase transformer when supplying maximum load. Okay, and the copper loss, PCU, the formula for copper loss, remember copper loss is due to REQS. So if it was a single-phase transformer, you just have IS squared REQS, but this is a three-phase transformer, so there should be a 3 in front, and the current IS through this resistance REQ is the IS phase. So 3 IS phase squared times REQS. So we substitute the value. IS phase magnitude is 45 squared times REQS 0.058, and that gives us a copper loss of 352.35 watts. And the core loss formula, normally you'll have VP phase over A squared divided by RC prime. But this time is a 3-phase, so 3 VP phase over A squared divided by RC prime. And VP phase over A magnitude is 252.38 squared, RC prime 143.47, and that gives us a core loss of 1331.9 watts. Now, using all these three values, we can then calculate the efficiency. So now the efficiency of the transformer can be calculated using the formula. Efficiency is P out over P out plus PCU plus P core, and we always write the efficiency as a percentage. So substituting the values for P out, 28141.4, PCU 352.35, and P core 1331.9. So we get finally an efficiency of 94.55%. Okay, so to summarize this example, from test A and test B, you must be able to identify which is the open circuit test and which one is the short circuit test. From the open circuit test, you must also find on which side were they conducted for both tests. Then from that, we got the equivalent circuit parameters RC prime, XM prime, REQS, XEQS, because in this example, both tests were done on the secondary side. Once we have the equivalent circuit parameters, depending on the load condition, you should identify VS phase. From the load condition, you should find IS phase, and then from the KVL of the equivalent circuit, find VP phase over A. Now the reason for VP phase over A is so that we can find the voltage regulation, which is VP phase over A magnitude minus VS phase magnitude divided by VS phase magnitude, and multiply 100%. Okay? So this normally is what we find in the transformer. We want to know the voltage regulation, and then we also want to calculate the efficiency of the transformer, and to find the efficiency we need the output power, the copper loss and the core loss, and the formulas for output power, copper loss and core loss is as shown here. So please make sure you're aware that in the three-phase transformer, for the power calculations, there must be a 3 in front, and you must use phase voltages and phase currents in the equations. So please study this example for your preparations for the final exam. Thank you. Bye-bye.